So today we are going to see in this tutorial class finite difference method and spectral method. These are the two things. Already we have seen finite volume method. Okay. So for that one again we are going to consider a computational domain like this. You can see now. So our computational domain consists of a rectangular region bounded by walls. So here we are considering stress-free boundary conditions. Not in the previous case it is rigid boundary conditions. Now we are considering here stress-free boundary conditions. Okay. Of course, these things are already elaborated, I think. So in this one, what is it? The temperature difference between the hot bottom boundary and the cold top boundary drives the flow. So this flow is driven by temperature. Okay, that is what it is given. And the left and right boundaries are insulated boundaries. Okay. 1 second. Okay, so yeah, side boundaries are thermally insulating. That is, there is no heat flow through them. Fluid flow and the gradients only in two directions. That means we are assuming this axisymmetric case along the y direction. So only in the z and x direction. Now we are going to find out this flow with respect to the streamlines and isotherms. Already we come across about the streamline definition in fluid dynamics. How to write it? Let us see that. Next slides will tell you that. Okay, now the basic governing equations from the starting of the course we are seeing that the first one is by assuming the flow is incompressible fluid, not flow. Fluid is assumed to be incompressible fluid. So we come into this continuity equation of the form divergence of that velocity vector equals to 0. Here for the velocity vector we have two components. Okay, let us derive that also. The next one is Navier-Stokes equation. IA is the Rayleigh number and PR is the Prandtl number. Okay, first term is that is equation number 1.2. The left hand side first term is the unsteady term and right hand side first term is the nonlinear term and third one is pressure and next one is the temperature. The source term we called in the finite volume method. Okay, the next term is diffusion term. Diffusion term is multiplied. Of course, this is in the non-dimensional form. Not dimensional form, it is in the non-dimensional form. If you go for this commercial softwares like ANSYS, Fluent, otherwise also OpenFOAM, etc., you have to give the values in terms of the dimensions. Velocity meters per second, like that you have to give. Length in terms of millimeters, meters, etc. But here we are giving them in the non-dimensional form. How to non-dimensionalize? We are seeing every day, isn't it? Different scaling factors we are seeing. So this parameters also occurring in a different way. Okay. The next last equation is the heat equation, and again we have the nonlinear term there, isn't it? Right hand side first term is the nonlinear term. In this tutorial, let us start with the linearizing this one. Okay. All variables are non-dimensional and the domain is considered from x is varying from 0 to a. This one. You can see here now x is varying from 0 to a and the vertical direction is varying from 0 to 1. Okay, 0 to 1. So we are going to give different values for a and we are going to simulate the flow here. Okay, that is the idea behind this. And a is nothing but our L by D, where D is the depth. L is the length, okay, and A is known as the aspect ratio of the box. Usually in some papers we used to denote with gamma. Even in finite volume method also we have the symbol gamma is there. Is it along with the diffusion coefficient? Last one, del square V is there. Last one, del square V bar actually. It is multiplied with gamma. Okay. There in the finite volume method we have used. Just to relate those two things I am teaching you like this. Okay. Now already we have seen the basic definition of the Rayleigh number is given to be like this. G naught, that is G is a gravitational vector. It is a vector and we are considering only in the z direction and alpha is the Thermal expansion coefficient delta T is the temperature difference between the bottom and top layers. Then D is the depth of the layer, and nu is the kinematic viscosity, kappa is the thermal diffusivity. And PR is defined like this. These are the basic things. Now let us move on. Now, so we are, as I said before, we are considering the linear stability here. So as I said before, two methods, finite difference and spectral method. So finite difference is generally used everywhere. What is a numerical technique used to approximate derivatives by discretizing differential equations, the basic definition. So in linear stability analysis, finite difference method is applied to convert differential eigenvalue problem to a matrix eigenvalue problem. So we are going to convert that to find out the stability of the flow, at which number, I mean the parameters, Rayleigh number and Prandtl number. Mostly Rayleigh number deals with the temperature difference, which exactly for what values the flow is becoming convective. Onset we are going to find out, based on this eigenvalues. Now we are going to do that numerically. MDM also describes solving the equations computationally. Now coming to spectral method, what it tells us, again we are solving the equations only by transforming them to a simpler form using basis functions. That means trigonometric functions we are going to use. We are going to rewrite this velocity dependent variable in terms of sine and cosines. That is trigonometric function. Here it is given. The spectral method is based on Fourier expansions. Let us see that how it has been written. Coming back, we want to remove that pressure term, because for the pressure there are no boundary conditions. How to deal with the pressure? To remove that one, we are going to introduce this vorticity vector. It will already, vorticity is defined as curl of velocity. Curl of velocity, that is only. Then it is a two-dimensional problem, so we have that term. If you write down in this curl how to do, where you will get the values. Here it is shown. This is vorticity is given to be like this. Vorticity is defined in terms of the vectors like this. Vx is usually we denote u, vy is v. And vz is w. Here we have considered only x and z. That is why u and u and w is appearing here. Vx and vz. Any doubt in this slide? Now, based on that one, now what we are doing, as I said before, we want to eliminate the pressure. So what we are doing is, we are taking the curl of Navier-Stokes equation, whatever is given, then it will reduce to, after some calculation, it will reduce to this one, equation 1.7. Now what is our aim? We are going to find out omega from this equation. From this equation we are finding out omega, and after updating with the vorticity, fluid velocity is updated with respect to the stream function. How it is defined stream function? 1.9 tells here. Basic definition only. Velocity components u or vx equals to negative of dou c by dou z, and we are choosing this stream function such that it satisfies the continuity equation. Divergence of v bar will be 0. If you substitute that one, then automatically you will get, this one also. It will get satisfied. And what is the relation between vorticity and stream function is? It looks like a Poisson equation. So now we are going to find out the vorticity, stream function, temperature. Then from that, once we know vorticity or stream function, we can able to find out the velocity. Our aim is now to solve for the dependent variables, this one, vorticity, stream function and temperature. Now let us move on to the spectral method. Already we want to find out these three things. These three dependent variables, we are decomposing them into trigonometric functions, that is Fourier series. So you can observe here, this is a function of x and z. Already our domain is a rectangular domain. We have taken x-axis and z-axis, and also we are taking time also here. Now we are rewriting that in terms of the series form. Okay, Tn, again cosine is in terms of x, and the two variables along with this. Okay, and n is varying from 0 to n. How many grid points we are going to take? That much value here. Similarly, we are writing omega and psi here. We are choosing sine and cosine such that it will satisfy the boundary conditions. Okay, what is the boundary conditions here? We have considered as stress-free boundary conditions. Okay, yeah. N represents the wave number of the Fourier modes. So, how many modes we are going to consider? That much accuracy we can get. Yeah. So, the truncation level. Some more explanation for the notations here. Truncation level. This is the maximum mode number included in the spectral expansion. As I said before, if you include more number of modes, then accuracy will definitely increase, isn't it? N equal to 0 to nn here. You can go from n equal to 0 to 1 also. Then here t1 t naught z comma t cos n pi x by a plus t1 z comma t cos n pi x by a, like that we will get two modes. We call them as two modes, three modes, etc. Similarly for the vorticity and stream function. Okay. Yeah. The temperature expansion starts with n equal to 0 because the cosine term for n equal to 0 is non-zero. If I substitute n equal to 0 here, you see, n equal to 0, cos 0, 1. That's what it is written here. Represents the horizontal average of the temperature at the given vertical position z and time t. Only we have here the variable if n equal to 0, temperature is a function of z and t only. If n equal to 0 here, vorticity and this stream function becomes 0 here, satisfying the conditions. That is what, okay, here. Next, n equal to 1 mode represents half wavelength that spans the length of the domain. So, n equals to 1 mode. So, for every mode we have an explanation. N equal to 1 mode represents half wavelength, okay. Aspect ratio already we have seen, L by D. The length along the x direction divided by depth of that layer, depth of the that domain which we have considered. Next, wave number is defined as n pi by a. Okay. If we, how many modes we are going to consider, based on that, this wave number also differs. Okay. This represents the number of radians per unit length for a given Fourier mode. Okay. This is our language. We call modes, etc. here. Yeah. So insulating boundary conditions. Already we have seen we are, and the side walls will have the insulating boundary conditions. That is what is given. Yeah. It is automatically satisfied by the cosine expansion of the temperature because the derivatives of the cosine expansions are 0. Left side and right side. X equal to 0 is the left side. X equal to a is the right side. Okay. Aspect ratio. Similarly, impermeable condition. Then comes stress-free condition. How it is mathematically given here is represented here. Vx is in terms of stream function, it is given like this, and it should be the impermeable condition. That is, it is vanishes. And the stress-free condition is, it is given like this. Mathematically, it is given. Okay. Coming to the next step, what we are going to use is here this condition, orthogonality condition. So sine n1 pi x by a, sine n2 pi x by a into dx if n1 equals to n2. Then it will have this value. Otherwise, if they are not equal, then it will have the 0 value. Orthogonality condition we come across about these two. Similarly, we are going to write down for the cosine function also. See here for the cosine terms also. Here for the sine. Next one is for the cosine. Okay, now what we are going to do here is the spectral expansions of T omega psi. That is the original equations. We have seen now here. This one. This is the omega equation. And the temperature equation is, we started with that one. This one. and then T, omega and psi. Okay, psi is, yeah, this one. The spectral expansion of this dependent variables are substituted. What are the spectral expansions? This one. This spectral expansion. Instead of T, you are writing them in the series form. Instead of omega, you are writing down that in the series form. Instead of psi in the series form. Where? In the Navier-Stokes equation. Okay. You will land up the equations like this. Because you have to take the derivatives also. The partial equations have the derivatives also. You have to substitute them and you will land up like these three equations. These are the final equations. Okay. Now we are going to write down the code to solve this. To solve what? Temperature, vorticity and psi. Okay. So the boundary conditions also how it should be written. That is what the explanation here. Isothermal boundary conditions means uniform. Iso means uniform, isn't it? Uniform thermal boundary conditions for the mean temperature perturbation T naught equals to 0. T naught means initial temperature. Initially it is 0 at z equals to 1 and T naught equals to 1 at z equals to 0. Z equals to 0 means bottom boundary. Then top boundary is z equals to 1. Okay. For n greater than 0, Tn equal to 0 at both top and bottom boundaries. Okay. Next one is impermeable boundary conditions. So for all values of n, psi n will be 0. Both boundaries, bottom and top boundaries. Okay. The next one is stress-free boundary conditions. This also already I have shown, and we are writing in terms of this spectral expansions. Okay. Now Fourier coefficients Tn, omega and psi n for n greater than 0 vanish at the top and bottom boundaries. Okay then. So you are going to write down that in terms of the Fourier expansions. The equations are written in terms of the Fourier expansions. That is like this. Now we are going to apply the finite difference method. Already we know what is a finite difference method. We are going to apply here central difference method. Isn't it? And this term will not be there because we are doing the linear stability analysis. So automatically we are taking out these two terms, this one and this term. Then how to write the finite difference method, isn't it? That we have seen in the finite volume method itself, that is difference between the next step minus the current step divided by the grid spacing is delta T. Here you see, that is what it is written. Okay, this is the simple expansion for the using the Taylor series. Taylor series expansion by assuming the functions are continuous. Now that is what it is written here. For k plus 1, here k minus 1. Now adding and subtracting and doing some calculations, we can get first order derivatives, second order derivatives. That is what it is written. So first order derivative is, this is a central difference method. Nodal point k plus 1 minus not k minus 1 divided by 2 deltas. So this is a central difference method. Similarly for the second order derivative also central difference method is given. Now for that time it is using this, what is the method? Adam, somewhere it is written. Adam-Basforth method. Okay, using that one, time is discretized for all the dependent variables. That is, we want to know the value of the next time step. Instead of jumping too far, we are moving half interval, then again half interval. So t plus delta t by 2. Okay, that is what it is written. So it is the average of this one. 3 minus 2 divided by 2, so you will get back this one. That is the idea behind this. Okay, so we are substituting this one here and we are writing, see, delta t by 2, 3 gt minus gt minus delta t. Instead of t, we are going to substitute this t values, whatever we are going to know that. Yeah. So we are, till now we are dealing with this one, was general finite difference formulation, and for the time. These things are for the space derivatives. Z is a space coordinate and t is the time coordinate. Okay. Next one, how to solve this Poisson solver. Because what is the formula we had? Omega equals to, omega equals to, where is it? Minus del square psi. How we are going to discretize this one? How we are going to discretize this one? Once we know the value of omega, we can know the psi value, we can go back, etc. Either psi or omega we want to know. Here. This is based on the spectral one. Already we have defined here. Here you see how omega is defined. You are going to substitute this omega and psi into that equations. Omega equals to minus del square psi. There you have to substitute these values and get this equation. And then for the derivatives you are applying the Cannon difference method. Okay. After this we will get the values at the nodal points k minus 1, k plus 1. How to solve that one? Using k minus 1, k plus 1. So tridiagonal matrix solver. Okay, that's what it is written. That's what it is written here. You see, subdiagonal, diagonal, superdiagonal. With this, unknowns and right hand side is known values. Solve it and get the answer. Okay. So what are the coefficients also it is written here? Yeah. Subdiagonal values, everything. Now the equations. Yeah. By neglecting the linear, non-linear terms, the equations are written here. These are the three equations already I have shown you with the conditions. Top and bottom conditions. Okay. Boundary conditions. Yeah. So up to this we are going to solve this one and we are going to see the solutions. Analytical solutions if we do, we will get the critical numbers. Okay. Later once we finish this Fortran code, we will move to the analytical solutions, that is finding out the critical Rayleigh number if time permits. Okay. First we will do this one. The linear code is available, we will do that one. Okay. Already we have done some work, we will present that one. Let us see that whether online Fortran is working. If anybody has Fortran, it's okay. Otherwise also you can try this code in online Fortran. Nowadays online C, online C++, Java, everything is available. No? I remember I tried online also. Is there? No, we have done in Fortran this code. Yeah. You see? Okay then. Okay. Yeah, we will try that code now. Yeah. Okay, stop. Okay. So the how to apply the spectral method. Okay. We'll do that. First to see that PPT. If any doubts are there, you ask us. Then we will move to the code. How to do that one. Then how to plot them. These are the three things we are going to do today. Okay. If you understand, you can go for the non-linear thing.
Good evening, everyone. I am Preeti. I am from SR University, Warangal. Now I am in the first semester of my PhD program. My supervisors are Dr. G. Ravikira and the co-supervisor is C. Balarama Krishna. I'm just started my coursework. In my coursework, I'm studied about the biofluid dynamics and as well as numerical solutions of differential equations. I have not decided any particular program to in research, but I have planned to do in the fluid dynamics with non-Newtonian fluid. Okay. Now I am taking one of the tasks given by the Sergey sir, that is 1.4.2. Here the momentum of equation and continuity equation is I am deriving here. That is this is the unsteady term. And this is viscosity term. Sorry, this is convecting term. And this is viscosity term. And this is density. This is the body force. This is my equation 1. This is the momentum of the equation. And second one is continuity equation. This is equation 2. Now given condition is U bar equal to omega cross R cross plus V bar. This is equation 3. Now I am substituting equation 3 into equation 1. That is dou U bar is here, given condition, that is omega bar cross R cross plus V, that is dou by dou t, plus U bar is same, omega bar cross R cross plus V bar and nabla. Again U bar is omega cross R plus V bar. This is the right hand term. The left hand term is mu nabla square. U is omega cross R cross plus vector V. This is my equation 4. Expanding this, dou V bar by dou t plus dou by omega cross R cross by dou t plus V bar omega cross R cross plus delta plus omega cross R cross plus V bar cross V bar dot delta plus omega cross R cross. Now mu delta square this is equation 5. Now I am doing the cross product of this omega and R bar. That is, this is in the Z direction, that's why I am taking omega k, that is xy plus yj plus zk. This is the I and j will get k and I will get j. This is the opposite rotation will get minus, that is y I cross product, this is 0. Now omega cross r is I is here minus omega y and j is omega x and k term is 0. Now these equations I am substituting in. Now from equation 5, omega cross r cross delta v bar, we can, by solving we can write as omega v bar and v bar dot delta omega cross r equal to omega cross v bar omega cross r value is 0. These are substituting in equation 5. We get that dv by dt and here differentiating with respect to t, then we'll get 0, that is v bar plus delta v bar plus omega plus v bar plus omega plus v bar is equal to mu dot delta square minus gradient p plus density. Now that is delta v bar plus 2 the plus v bar equal to mu delta plus v bar minus delta p by f delta p. This is the required equation of the moment. Now I am deriving the continuity equation. We already given that mu bar is plus v, substituting is omega plus v equal to 0 cross r bar plus v equal to 0. This term is 0. Final term is, this is the equation of the continuity.
Units. So here we've got dv over dt, here we've got v double v, and here something bad happened.
From the we have substituted this equation in the equation 5. This is from the equation 5, that is there.
Yeah, I got it, but maybe it's not plus here. Because omega plus v, yeah, it's possible. That's from the consideration of dimensions. Yeah.
Cross.
Now it looks better. Now the dimensions are correct. Okay, okay, thank you. So by this, could you say some words by all these different relations and transformations? So what do we prove? Yeah. Continuity equation
Continuity equation
for another representation of velocity for a
Coriolis force.
yeah, for a
Planetary
tension
force
system.
square.
Okay, thank you.
Is there any questions? Thank you.